we've got different types of lines that we're looking at. Okay? We have talked about perpendicular bisectors. What's a perpendicular bisector? What's it mean to be perpendicular?
It's equidistant from the endpoints of the segment.
Okay, that would be something that's in the middle, equidistance from the endpoints. Okay? What's it mean to be perpendicular in any setting? Okay, you're doing it with your hands. Okay, she's doing this. So when something is perpendicular, it forms a right angle. And to bisect something is what, Madeline, you said. Okay, to bisect something is to cut it in half. So if I have a perpendicular bisector, in a drawing, I'm going to see the side cut in half, and I'm going to see a box right here. To designate that the side has been cut in half, you're going to see tick marks on both sides of that line. Okay, that line doesn't necessarily start at a vertex, and oftentimes it doesn't. Okay, and so if I were to extend this out, okay, if I bisect, put the perpendicular bisector in for each side. So we do another one here. That's perpendicular, and yes, these are by hand, so there's going to be some mistakes here. These are the markings that you're going to see on the drawing. You're going to see the fact that all the lines are perpendicular at the sides, and they bisect each side. And they meet at a point in the middle, and what point did we call that? What did we call that point? You got to know that.
Isn't it like intercenter?
That's, yep, you're on the right track, but it's not the incenter, it was called the circumcenter, okay? That is the circumcenter. And what that does for us is that distance from that point to any corner of that triangle is equal. It's the same distance, okay? Then we also talked about, after perpendicular bisectors, what was the next one we talked about? We had angle bisectors. Now the angle bisector does start at the vertex, and you see angle marks, arc marks, to tell you that that angle has been bisected or cut in half. And then here you had an angle bisector, so you saw arc marks to tell you that that angle had been cut in half. Okay, and you had arc marks to tell you that that angle had been cut in half. And those angle bisectors, okay, these were angle bisectors. The only way that I know that these are angle bisectors is because I see the arc marks. If they're not there, then you don't know the angle's been bisected, unless the directions tell you that. But they are going to meet in the middle, and as Hannah said, that's called the incenter. And what I knew about the incenter was that the distance from that point to the sides, and that is a perpendicular, so it's a distance directly to the side on a perpendicular. That's why you saw, still in some of the drawings, that's why you saw that perpendicular box there. Because the distance from the incenter directly to the side on a perpendicular is equal. That would be the same. Okay, and then right before break we talked about altitudes. An altitude is a perpendicular to the opposite side. So just like the perpendicular bisector, it's perpendicular at the side. However, this one always starts at a vertex. And it is not cutting this side in half. Not very often will it do that. Okay, that is an altitude. And we don't do a whole lot with altitudes. They will meet, and that's called the orthocenter. And there's no significance about the orthocenter, so we don't do a lot with that. But we did talk about altitudes. And then the last one, and I'm not going to use a right triangle yet. The last one, and we're going to spend more time on this today, is what a median is. What's a median? What is the word median in math? Middle. Okay? If we find the median of a group of values, we're lining up the numbers and we're finding the one in the middle. What a median in geometry is when you start at a vertex and you draw a line to the middle of the opposite side. So you're going to see tick marks in that drawing, showing you that that line is cutting that side in half. So again, it has some similarities to the perpendicular bisector, because you're going to see tick marks here, because the side's been bisected. You're going to see tick marks in some of the median drawings, because that's going to the middle of the opposite side. And if I do the same thing for each one of these, okay, that median meets at a point, and that point is called the centroid. Okay, that's the centroid. That's what we've talked about so far. So if you don't remember any of that, look through your note packet. Look through some of the worksheets that you've gone through. Those vocabulary words are going to be important for you to know. What you're going to work on today is a little more with the median. You're going to take a drawing like this and you're going to fill in what the pieces are, what the different distances are. Now this is the centroid again, and the centroid does not, these are not going to be equal lengths on either side of the centroid. It's a 1/3, 2/3 relationship. 1/3 is the shorter segment, and 2/3 is the longer segment. Okay, so if I were to take any median, here's a median right here. And if I were to tell you that that distance of that median, let's say that's 39 for a total distance. You want to break that into thirds, because the shorter piece, and when you look at the picture, you're always going to be able to tell this looks shorter than that one, doesn't it? So the shorter piece is 1/3 of the total, and the longer piece is 2/3 of the total. So how do I come up with 1/3 of my total? How would you come up with 1/3 of a number? Divide it by 3. That's right. If you want 1/3 of something, you divide it by 3. So if I take 39 and I divide it by 3, I get 13, which would tell me that this shorter piece has a distance of 13 units. Now, how does 1/3 compare with 2/3? How much bigger is 2/3 than 1/3?
1/3.
It's how much bigger?
1/3.
You think it's 1/3 of the distance?
Well, it's 1/3 bigger than 1/3.
Okay, so you'd be adding them together, right?
Yeah.
So if this were 1/3, then I would have to add it to itself to get the 2/3 part. So this piece right here would be 26. Now I want you to look at those numbers again. How much bigger is the 2/3 piece than the 1/3 piece? Would you say it's 13 bigger, or would you say there's a different, it's true, but would you say there's a different relationship?
It's double.
It's double. That's right. So 2/3 is twice as big as 1/3. So if you know one of these pieces, you will be able to figure out the other one by using that relationship. The smaller piece, if you double it, you'll have the bigger piece. If you know the bigger piece, if you cut it in half, you'll know the smaller piece. Okay, that's your 1/3, your 2/3 relationship. So if I said that this piece, let me switch colors here. Let's say this piece right here has a distance of 30. What would the shorter piece on that be? 10. You take that and you divide it by 3. So that shorter piece would be 10. That's 1/3 of it. So how would I get the 2/3 piece? You would double it and you would get 20. Make sense?
Yes.
Okay, that's your relationship between your 1/3 and your 2/3. Okay, and then one other thing that I'm not sure we talked a whole lot about is when you're looking at a graph, if I were to put this on a coordinate plane where I can tell you what the coordinates of these vertices are, let's say on the coordinate plane this is like 2, 3, this is going to be 8, 3, and this would probably be something like 5, 12. If I can put a triangle on a coordinate plane where you can tell me what the vertices are, you can find the location of the centroid by averaging the coordinates. Okay? So if I take the x values out of all of the vertices, if I average them, I'll know where the centroid is. How do you average a set of numbers?
Add them all together and then divide by how many.
Add them together and divide by how many there are. So there's always 3 vertices in a triangle, so you're always going to be dividing by 3. But if I said 2 plus 5 plus 8 divided by 3, I would end up with 15 divided by 3. So it has, the centroid would have an x-coordinate of 5. And then you do the same thing for the y-coordinates. You take the y-coordinates, you add them together, and you divide by 3. So I would take 3 plus 12 plus 3 divided by 3. That would be 18 over 3, which is 6. So if this were on a coordinate plane and those were the 3 vertices, that's where the centroid would be located at 5, 6. You can just do that by averaging the corners. Okay, I've got a worksheet for you to work on. And you're going to be finding those distances.